Okay, so so delta t, the time interval measured in the a time interval measured in the Bob's reference frame. Okay, in this case it's the Earth frame. It is equal to gamma, which is this ratio 1 over square root of 1 minus beta squared, beta equals v over c, times delta t prime squared, which is the time interval measured in Anna's rest frame, which is the one that's moving with the cart. Okay, so we can think of this round trip here as sort of a light clock. Okay, it's ticking off a certain amount of time, so that's like one time interval for the light to travel up to the mirror and back. Okay, and what we've done is we've basically shown that the time that Bob measures is longer than the time that Anna measures by this factor gamma. And remember, if you look at this ratio, if you look at gamma, beta is the ratio of the velocity of the cart relative to the speed of light. Okay, so if you look at this, gamma can only be is always greater than or equal to 1. Okay, and so the time interval here measured in Bob's frame is always going to be longer than that measured in Anna's frame, and that's the time dilation that we discussed in the previous lecture. Okay, so just to give a better feeling for the ranges of gamma, let's consider the limits on beta of very small beta that is very close to 0. Beta is much less than 1, which is equivalent to saying that the velocity of the moving frame is very small compared to the velocity of light. And also the sort of inverse limit, beta is approaching 1, and that's equivalent to the velocity of the moving frame approaching c. Okay, so in this first limit, beta very small, then what we have is that, remember, gamma is equal to this expression, and so this, if beta is very small, we can basically neglect beta squared compared to 1, and so we get that gamma is approximately 1. Okay, and so in this limit, delta t is equal to, which is equal to delta t prime times gamma, which is approximately equal to delta t prime. Okay, so this is the simple case. Oops, let me not move over there. This is the simple case of Galilean relativity that we discussed a few lectures ago. So this is relativity where time is time. Okay, so at very small speeds, then Einstein's special relativity converges to and agrees with Galilean relativity, which is satisfying since we know that works in our everyday life. Okay. The opposite limit, beta approaches 1. If beta is very close to 1, then this denominator here is very close to 0, and so we get that gamma approaches infinity. Okay, and in this case, delta t also approaches infinity. Okay, and so this just says that larger relative velocities lead to more time dilation. Okay, now here I've written down just a table that for different values of beta, increasing from 0, 0.5, 0.75, 0.9, 0.99, 0.999, and 1, what the corresponding values of gamma are, and you can see it's completely nonlinear. Okay, gamma stays close to 1 for up to pretty high speeds, and then it starts to get very large very quickly.